minus 15 seconds. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission.
January 28, 1986. For most Americans, this wasn't just another rocket launch. Across the United States, millions of people were watching live television. Schools paused lessons, teachers rolled TVs into classrooms, and news stations interrupted normal programming. Because onboard Challenger was Krista McAuliffe, a normal school teacher from New Hampshire. NASA had spent months turning the launch into a national event. The Teacher in Space program was meant to inspire children and restore excitement around the Space Shuttle program. By the mid-1980s, NASA wanted the shuttle to feel routine, safe, almost ordinary. Not like the dangerous experimental rockets of the 1960s. The shuttle was marketed as the future, a reusable spacecraft that could launch frequently, lower costs, and make access to space almost industrialized. And politically, that image mattered. The United States was still deep in the Cold War. Technological superiority was tied directly to national prestige. Every successful launch symbolized American engineering dominance. But behind the scenes, the shuttle program was under pressure. Launch schedules were slipping, costs were increasing, and NASA had promised far more launches per year than it could realistically achieve. And Challenger had already been delayed multiple times before January 28th. Another delay would be embarrassing, especially now that the entire country was watching. But during the night before launch, temperatures at Cape Canaveral dropped lower than almost anyone expected. Ice formed on parts of the launch pad, and engineers became deeply concerned. Some believed the shuttle should never leave the ground. 73 seconds after launch, Challenger exploded live on television. 7 astronauts were killed. And the horrifying part is, this disaster could have been completely preventable. To understand why Challenger exploded, we first need to understand how the shuttle itself worked. Unlike traditional rockets, the Space Shuttle used 2 massive, solid rocket boosters attached to the sides of an enormous external fuel tank. These boosters generated most of the thrust during the first phase of launch. And unlike liquid-fueled rockets, solid rocket boosters cannot simply be shut down once ignited. Once they start burning, they keep burning, which means reliability is absolutely critical. Now here's where things become important. Each booster was built in cylindrical sections that had to be assembled together before launch. And between these joints sat rubber seals known as O-rings. The job of the O-ring is simple. Prevent superheated combustion gases from escaping the booster joints. But the environment inside a rocket booster is insane. Temperatures inside the booster could exceed 3,000 degrees Celsius. Pressure built up almost instantly during ignition, and the joints physically flexed under enormous mechanical stress. The O-rings needed to respond immediately. When ignition occurred, pressure would force the rubber into gaps inside the joint, creating a seal before hot gases could escape. But there was a problem engineers had already noticed during earlier launches. The colder the weather became, the slower the O-rings responded. Rubber is viscoelastic, meaning at warmer temperatures it remains flexible and elastic, but as temperature drops, it stiffens. Its ability to deform quickly decreases dramatically, and in engineering terms, response time mattered enormously. Because during launch, the seal had fractions of a second to fully seat itself before combustion gases reached the joint. If the O-ring reacted too slowly, hot gases could blow by before the seal formed properly. This phenomenon had already been observed. Previous launches had shown erosion on O-rings, black soot passing through joints, and signs of partial sealing failure. To several engineers at Morton Thiokol, the company responsible for the boosters, these weren't minor anomalies. They were warning signs, especially to one engineer, Roger Boisjoli. For months, Boisjoli had warned internally that low-temperature launches posed a catastrophic risk. Not a small risk, not acceptable degradation, a catastrophic failure. And now Challenger was preparing to launch in the coldest conditions the shuttle program had ever experienced. Temperatures overnight reached around -1 degree Celsius, far below conditions where engineers had confidence in the seals. The terrifying part is that NASA did not possess hard experimental data proving the O-rings were safe at those temperatures, because the shuttle had never launched that cold before. In other words, they were entering unknown territory. The night before launch, engineers and NASA officials held a now famous teleconference. And this conversation would later become one of the most controversial engineering management failures in modern history. Engineers from Morton Thiokol strongly argued against launching Challenger. They presented data showing a correlation between low temperature and O-ring damage. Boisjoli and others warned that the seals might not function properly in the cold weather. Some engineers even recommended not launching below approximately 53 degrees Fahrenheit, around 12 degrees Celsius. But Challenger was scheduled to launch at far lower temperatures. NASA officials pushed back aggressively, partly because the data was incomplete, and partly because delays were politically and financially painful. The shuttle program already looked unreliable. Media coverage was enormous. Schools across the country were prepared to watch the launch live the next morning. And over time, something dangerous had happened inside the shuttle program. Management had become psychologically accustomed to risk. Previous launches had shown O-ring erosion. But the shuttle survived anyway, so instead of interpreting the damage as evidence of danger, many managers began treating it as normal. This phenomenon is sometimes called normalization of deviance. A system slowly accepts dangerous behavior because disaster has not happened yet. The absence of failure becomes interpreted as proof of safety. Eventually, under pressure, Morton Thiokol management reversed their recommendation. The engineers were effectively overruled. Launch approval was given. And according to later accounts, at least one engineer present at the launch site became so disturbed by the decision that he couldn't watch the launch itself. The next morning, ice covered parts of the launch structure. Engineers worried not only about the O-rings but also about falling ice damaging the shuttle during ascent. Still, the countdown continued. At 11:38 a.m., Challenger launched. Initially, everything appeared normal, but cameras later captured something chilling. Almost immediately after ignition, small puffs of black smoke emerged from the right booster joint. The O-rings had failed to seal instantly. For a brief period, aluminum oxide particles from the burning fuel partially plugged the gap. Essentially, the rocket temporarily sealed itself by accident and pure luck. But around 58 seconds into flight, aerodynamic forces intensified as Challenger passed through strong wind shear. The booster joint flexed again. This reopened the leak. A jet of flame escaped sideways from the booster. The flame began burning directly into the external fuel tank, specifically near the attachment strut connecting the booster to the tank. Then, disaster became inevitable. The flame ruptured the external tank containing liquid hydrogen and liquid oxygen. These cryogenic propellants mixed violently, and the shuttle structure rapidly lost integrity. At 73 seconds after launch, Challenger disintegrated. The Challenger disaster shocked the United States. NASA grounded the shuttle fleet for nearly 3 years. A presidential commission was formed to investigate what happened, and one member stood out immediately, physicist Richard Feynman. Feynman quickly became frustrated with what he viewed as excessive bureaucracy and attempts to soften the severity of engineering concerns. He believed NASA management was presenting an unrealistically optimistic picture of shuttle safety, and he became particularly interested in the O-rings. During the investigation, engineers quietly shared concerns and technical details with him. Many reportedly felt management had ignored or suppressed engineering realities for years. Then came one of the most famous moments in engineering history. During a televised hearing, Feynman placed a sample of O-ring material into a glass of ice water. After a short time, he removed it and squeezed it with pliers. The rubber remained compressed. It had lost elasticity. In a single visual demonstration, Feynman showed the world exactly why cold temperatures mattered. At the end of the investigation, he included a statement that became legendary. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. That sentence perfectly summarized Challenger. The disaster was not caused by one failed component alone. It was caused by organizational pressure, schedule pressure, political pressure, communication failures, and management overriding engineering concerns. And what makes Challenger so unsettling is how modern the story still feels. Even today, engineers across countless industries warn about risks that organizations choose to ignore. Most of the time, disaster never comes. But occasionally, physics wins. And when it does, it doesn't care about politics, schedules, or public relations.